Okay, so we were looking last time at the variational principles in mathematical problems. One of them is the eigenvalues of a real symmetric matrix. If you take a real symmetric matrix, then the eigenvalues satisfy a certain extremal principle. So let us look at a physics problem. A rigid body is rotated with a fixed uniform angular speed, and it's uniformly rotating and the angular speed is fixed. Let us normalize it. Let us assume that the angular speed is 1 unit. Now, how should I choose the axis of rotation? So, what is variable is the axis of rotation. We must now choose the axis of rotation in such a way that the rotational kinetic energy is maximized. So, how would one formulate this problem mathematically? So, that is the first issue. Now, recall from elementary physics courses that for a rigid body, it has the three moments of inertia and the three products of inertia. So, normally the moments of inertia are called Ixx, Iyy, Izz, and the products of inertia are Ixy, Iyz and Izx, and we get a 3 by 3 real symmetric matrix, and that is called the inertia matrix of the rigid body. Now, if omega is the angular velocity, then what is the rotational kinetic energy? The rotational kinetic energy is 1/2 of omega transpose I omega. So, we got a real symmetric matrix I, and we got to look at this quadratic function omega transpose I omega. So, the idea is that, so what we are going to now show is that to maximize the rotational kinetic energy, we must maximize omega transpose I omega subject to the constraint mod omega equal to 1. Remember that we have assumed that the speed, the angular speed is 1 unit, that the angular velocity has constant magnitude 1. So, that is a normalizing condition. So, we can now think of it in a variety of different ways. You probably, the first thing that comes to your mind is perhaps trying to use the method of Lagrange multipliers. So, you are looking at maxima minima subject to constraints, and you want to apply the method of Lagrange multipliers. I recommend that you should try this out. You try to do this problem using the method of Lagrange multipliers, that is maximize omega transpose I omega subject to the constraint mod omega squared equal to 1 by the method of Lagrange multipliers, and see what you get. We are going to take a slightly different route. Of course, it is ultimately equivalent to the method of Lagrange multipliers, but we will take a more basic perspective. So, let us first generalize the problem. Instead of looking at 3 by 3 real symmetric matrix, let us look at an n by n real symmetric matrix. And then let us look at the maximum and minimum or the quadratic function Ax dot x. Ax dot x means A is a matrix, x is a column vector. So, Ax dot x is x transpose Ax. So, you see that we have generalized the previous problem from the rigid body to an n cross n real symmetric matrix. So, our variational problem is to maximize the quadratic function x transpose Ax subject to the condition x1 squared plus x2 squared plus etc plus xn squared equal to 1. Now, we want to show that the maximum and minimum are both eigenvalues of A. The maximum of this quadratic function is going to be the largest eigenvalue, the minimum is going to be the smallest eigenvalue. And we are maximizing over what? We are maximizing over the unit sphere, x1 squared plus x2 squared plus etc plus xn squared equal to 1. Now, remember that the unit sphere is a closed bounded subset of Rn, and hence it is compact. It is compact, and the quadratic form x transpose Ax is a polynomial, and so is a continuous function. Now, we have got a continuous function on a closed bounded subset, namely the unit sphere. Its maxima and minima are going to be attained. So, these maxima and minima are going to be attained, and they are going to be unit vectors, and the points at which this maxima and minima are attained are going to be the corresponding eigenvectors. So, this is the program. Let us carry out this program. So, let us go to the proof of this result that I just stated. Now let us call the quadratic form QV. What is QV? QV is V transpose AV. As I mentioned, it's a polynomial in n variables, the polynomial in the components of V, and as such it attains its minimum at some point, say V1 on the unit sphere in Rn, as I explained to you. Now let us take another vector W, which is a perturbation of V. Namely, take V1 plus epsilon h. So the minimum is attained at V1. Now I disturb it, I move away from the minimum point to V1 plus epsilon h, where h is an arbitrary vector in Rn. Now V1 plus epsilon h is not a unit vector. So I divide by the length of V1 plus epsilon h and call it W. Now W is a unit vector. W is also a point on the sphere. But V1 is a point of absolute minimum. So Q of V1 is less than or equal to Q of W for all epsilon small enough. Alright. So now what is Q of V1? Q of V1, let us call it lambda 1, just for fixing ideas. Now what is Q of W? Q of W is V1 plus epsilon h transpose A V1 plus epsilon h, and then you have to dividing by V1 plus epsilon h norm squared and bring that denominator to the left hand side to clear the fractions. So what do we get? Q of V1 into norm of V1 plus epsilon h squared less than or equal to V1 plus epsilon h transpose A V1 plus epsilon h. Now we must expand the right hand side. V1 transpose A V1 will appear on the right hand side as one of the terms. But V1 transpose A V1 is what? Q of V1. Left hand side, norm of V1 plus epsilon h squared. What will happen when you expand it? V1 plus epsilon h dot V1 plus epsilon h. You're going to get a V1 dot V1, but V1 dot V1 is 1. So again Q of V1 will appear on the left hand side. So Q of V1 appears on the left hand side, it also appears on the right hand side. Cancel it out. So cancelling off Q of V1, what we get is the middle terms. Q of V1 into norm of V1 plus epsilon h squared, that is going to contribute the middle term. What is the middle term? 2 epsilon V1 dot h. 2 epsilon V1 dot h. But what is V1 dot h? V1 dot h is h transpose V1. So the middle term has been written down. So what do you get in the last displayed equation on the slide? 2 epsilon q V1 h transpose V1. Of course, there's going to be an epsilon norm h squared term. There's going to be an epsilon squared terms, and that epsilon norm h squared term has been thrown to the right hand side, as you see in the last displayed equation in the slide. Now let us look at the right hand side. Right hand side also will have an epsilon squared term, right? The right hand side will also have an epsilon squared term. What will the epsilon squared term on the right hand side? It is going to be h transpose AH. So these epsilon squared terms have been collected together. What about the epsilon terms appearing on the right hand side? It's going to be epsilon h transpose AV1 plus V1 transpose A epsilon h. So it's epsilon times h transpose AV1 plus V1 transpose AH. But remember, V1 transpose AH is what? AH dot V1 or AH inner product with V1. Now, A is a real symmetric matrix. So AH inner product with V1 is the same as H inner product with AV1 by symmetry. It is here that the symmetry is being used. And so V1 transpose AH is the same as H transpose AV1. And these two terms combine to give you 2 epsilon H transpose AV1. So let us bring the epsilon terms together. Let us keep the epsilon squared terms together. Okay, so we divide by epsilon. we divide by epsilon, assume that epsilon is positive. First assume that epsilon is positive, we divide by epsilon and let epsilon 0 through positive values. So what will we get? Look at the last displayed equation. We will get, the 2 will clearly cancel out. When the epsilon squared, you divide by epsilon and let the epsilon go to 0, the epsilon squared terms, their contribution will be 0 when epsilon goes to 0. So what will be left out? The 2 will cancel out. What will be left out now? You're going to get, let's see, H transpose into QV1 V1 minus AV1 less than or equal to 0. On the other hand, if I take epsilon to be negative, if I allow epsilon to go to 0 through negative values, when I divide by epsilon, the inequality will change. You will get the reverse inequality, namely H transpose into QV1 V1 minus AV1 greater than or equal to 0. So these two inequalities will together mean H transpose AV1 minus QV1 V1 equal to 0. But now remember, H was arbitrary. H was an absolutely arbitrary vector in Rn such that H transpose times this other vector is 0. So H transpose times a certain vector is 0 for all H, which means that this other factor must compulsorily be 0, which means that AV1 minus QV1 V1 must be 0 or AV1 must be QV1 times V1. Remember, V1 is a unit vector. And so what does this equation AV1 equal to QV1 V1 tell you? It tells you that QV1 is a eigenvalue and V1 is the corresponding eigenvector. In other words, the point V1 at which the minimum is attained is an eigenvector and the minimum value QV1 is the corresponding eigenvalue. That's what we have proved. I already told you the significance of the symmetry of A. We have used crucially that A is a real symmetric matrix. You must go back to this argument and you must locate exactly where and how we used the symmetry of A and we must flag it, and that's an exercise for you. Now we need to proceed further. We have captured the smallest eigenvalue, we have captured the minima and we have obtained the lowest eigenvalue. Now how do we get the next eigenvalue? That's the next problem. So to proceed further, let S be the intersection of the unit sphere in Rn with the hyperplane V dot V1 equal to 0. Okay. So we got this eigenvector V1 and now look at the plane perpendicular to V1. So now you work with this plane and you slice the unit sphere with this plane. Call the slice S. S is a closed subset of a compact set. The unit sphere is already compact. The plane is a closed subspace. The intersection of closed subspace is a closed subspace. Closed subset of a compact set is again compact. So S is again compact. S is again compact, and now you restrict the quadratic form QV on S. Look at the restriction of a continuous function. Again, it's continuous function. And so again the minimum on S. So now you minimize this quadratic form on S. This minimum is going to be attained again as before, is going to be attained at V2. And let us call the corresponding value QV2. Now we want to show that QV2 is going to be an eigenvalue and the corresponding eigenvector is V2. Now remember that earlier we minimized over the full unit sphere and now we are minimizing it over a proper subset. So if you have two sets T1 and T2, T1 is contained in T2. Minimum over T1 will be larger than the minimum over T2, correct? So this new minimum QV2 is going to be greater than or equal to QV1. So this QV2, which we are going to prove is an eigenvalue, is the next eigenvalue. The smallest eigenvalue will be QV1, the next eigenvalue will be QV2. So let's see how the proof goes. Again the same idea, we disturb V2 to V2 plus epsilon h. Now V2 plus epsilon h is not going to be a unit vector. So first we have to make it a unit vector. Divide by the norm. No, so we look at W equal to V2 plus epsilon h divided by norm of V2 plus epsilon h. But now the h must be chosen in such a way that this W must be in my subset S. So what is S? S is the intersection of the sphere with a plane which is orthogonal to V1. Now V2 is already orthogonal to V1. So now this H should also be orthogonal to V1. So we select our H in such a way that H dot V1 is 0. So we only look at those H for which H dot V1 is 0 and we construct this vector W. Now this W will also be orthogonal to V1. V2 is orthogonal to V1, H is orthogonal to V1, so V2 plus epsilon H will be orthogonal to V1 and so this W will be orthogonal to V1. So now W is a unit vector orthogonal to V1 and so Q of V2 is going to be less than or equal to Q of W because Q of V2 is the absolute minimum on S and W is lying on S. So again we do the same thing, we multiply the inequality by norm V2 plus epsilon H the whole squared. Norm V2 plus epsilon H the whole squared, just to clear the fractions, expand out as before, QV2 will cancel out, the epsilon squared terms have been collected together, the epsilon terms have been collected together, again symmetry of the matrix A will be used critically and we get this inequality 2 epsilon H transpose into QV2 V2 minus AV2 less than or equal to epsilon squared into H transpose AH minus QV2 norm H squared. Divide by epsilon and let epsilon go to 0. But epsilon can go to 0 through positive values or through negative values. We will get two opposite facing inequalities. Together it will become an equality. What happens to that equality? H transpose times QV2 V2 minus AV2 equal to 0. But now this is valid not for all H but only for H such that H dot V1 is 0. How can we conclude that QV2 V2 minus AV2 must be 0? We can only conclude that provided this last displayed equation holds for all H. We have proved that it holds for H orthogonal to V1. From there, how do we bootstrap upwards and show that that equality holds for all H? Let us see. Now suppose I take H to be V1. Suppose I take H to be V1, then what happens to that last displayed equation? QV2 is a scalar. So we get V1 transpose V2 or V1 dot V2. That is 0 already because V1 and V2 are already orthogonal by construction. Let us look at the other term, H transpose AV2. Remember, we have taken H to be V1. So what is V1 transpose AV2? V1 transpose AV2 is going to be the same as V2 transpose AV1. Again, we are using the symmetry of the matrix. So V2 transpose AV1 will be V2 transpose lambda 1 V1 because V1 was an eigenvector. Lambda comes out. So we get V2 transpose dot V1 which is 0 because V1 and V2 are orthogonal. So again the last displayed equation holds for all H perpendicular to V as well as H parallel to V. But any vector in Rn can be written as a sum of two vectors, one parallel to V1 and the other perpendicular to V1. That's always possible. And so the last displayed equation is going to be true for all H. And so again we can conclude QV2 V2 minus AV2 is 0. Again we see that QV2 is an eigenvalue and V2 is the corresponding eigenvector. So we have proved that the next iterate of minimizing over the proper subset S gives the next eigenvalue. It is very clear how to proceed further. Now to proceed further, we must minimize Q over the intersection of the unit sphere with two constraints. Now we again take a still smaller subset, namely unit vectors V which are perpendicular to V1 as well as V2, and you minimize over this smaller subset. Again the minimum will be attained, say at V3, and QV3 will be the next eigenvalue and V3 will be the corresponding eigenvector, and the process will continue. The process will continue as long as you keep getting a non-trivial intersection. Finally, the dimensions will keep going down and you will get a one-dimensional intersection, and that will be the last step in the process. And you would have constructed n orthonormal unit vectors which are eigenvectors of A. In other words, we have given a proof of the spectral theorem for a real symmetric matrix. Every real symmetric matrix admits an orthonormal basis of eigenvectors. This is one of the most important theorems in all of science. The spectral theorem of which you learn in linear algebra is one of the most foundational and one of the most important results in all of mathematics, all of science and all of engineering. And we are given a new proof of spectral theorem which is quite different from what you have seen in linear algebra. We have used calculus to prove the spectral theorem. So now let us go back to the question in physics. How should you choose the axis of rotation so that the rotational kinetic energy of the rigid body is minimized? The axis must be chosen to be along one of the eigenvectors of the inertia matrix. So take the inertia matrix. Remember that the inertia matrix is a 3 by 3 real symmetric matrix. It has 3 eigenvalues. Take the smallest eigenvalue and take the corresponding eigenvector and choose the axis of rotation to be that eigendirection, and the rotational kinetic energy will be minimized. If you choose the largest eigenvalue and align your axis of rotation in the corresponding eigendirection, the rotational kinetic energy will be maximized instead. So this is a variational characterization of eigenvalues. Now you might wonder, why is it that in this discussion on Sturm-Liouville problems, this linear algebra problem has been interposed? The reason will be clear presently, because what we have done, we have seen the spectral theorem from a variational perspective. The same variational principle underlies the Sturm-Liouville problems. The construction of eigenvalues and eigenfunctions of a Sturm-Liouville problem follows the same pattern of reasoning. There is the same variational principle that governs the construction of eigenvalues and eigenfunctions of a Sturm-Liouville problem with Dirichlet boundary conditions. We will see that presently. Now here is an interesting problem. Let me give a name to this QV. This QV is called the Rayleigh quotient. The same Rayleigh, Lord Rayleigh, theory of sound, who is the author of Theory of Sound volume 1, volume 2 that we have encountered before. This quadratic form QV is called the Rayleigh quotient. It's called the Rayleigh quotient because if V is not a unit vector, we should be looking at QV by norm V squared. But if we take a unit vector V, then it's simply QV. We have seen that if QV is an absolute minimum, then the corresponding vector is going to be an eigenvector. If QV is an absolute maximum, then it's going to be attained at a corresponding eigenvector. Can it happen that for a certain vector V, QV is a eigenvalue, but V is not the corresponding eigenvector? This cannot happen for the lowest eigenvalue and for the largest eigenvalue. This cannot happen. That we have just seen. But there may be other eigenvalues in between. Can it happen that for a certain unit vector V, QV happens to equal an eigenvalue and yet V is not an eigenvector? That can happen. That can happen. Let us see how to construct such an example. Let us take a real symmetric matrix with 3 distinct eigenvalues, lambda 1 less than lambda 2 less than lambda 3. We have 3 distinct eigenvalues. We know that QV must attain lambda 1 at the eigenvector V1. We know that QV must attain the eigenvalue lambda 3 at eigenvector V3. So now we got V1 and V3. V1 and V3 are mutually perpendicular unit vectors in R3. Look at V1 cos theta plus V3 sin theta. Look at V1 cos theta plus V3 sin theta and look at Q of V1 cos theta plus V3 sin theta. What is the value of this when theta equal to 0? It is simply QV1, which is lambda 1. What is the value when theta equal to pi by 2? It is Q of V3, which is lambda 3. So by intermediate value theorem, there must be a value of theta between 0 and pi by 2 for which Q of V1 cos theta plus V3 sin theta must equal lambda 2, the middle eigenvalue. But the corresponding point V1 cos theta plus V3 sin theta cannot be an eigenvector V2 because we know that the eigenvector V2 is perpendicular to both V1 and V3. So it can happen that the Rayleigh quotient can attain an eigenvalue at a vector which is not a eigenvector. This is a very important observation and we must be aware of this. Only for the largest and smallest eigenvalue will it be the case that the QV equal to lambda implies V is an eigenvector if lambda is an eigenvalue. That conclusion is true only for the largest and smallest eigenvalues. For the intermediate eigenvalues, the value of Q will be attained at these intermediate eigenvalues at points which are not necessarily eigenvectors. With this, I think we'll close this lecture. We'll continue with this in the next lecture.